Alright, this is the notes for section 7.5, geometric sequences. If you haven't done so already, make sure you pause the video at this time and read this section before continuing on. We've talked before, earlier in this course, on a couple different occasions, about sequences. And we primarily have looked at arithmetic sequences. Today what we're going to do is we're going to look at a different type of sequence, which we call a geometric sequence. And the first thing we want to do is look at the recursive formula for a geometric sequence. And the sequence defined for a recursive formula is the following. The rule for a geometric sequence is g sub n is equal to r times g sub n minus 1 for integers n greater than or equal to 2. Well, what does that mean? Well, r is a non-zero constant. Okay, so in the geometric or exponential sequence, with the first term g sub 1 and the constant multiplier r. So r is what we call a constant multiplier. Okay? In arithmetic sequences, we know that the difference between each term remains constant. However, in a geometric sequence, it's not the difference that remains constant, it's the ratio between successive terms that is constant. Okay? So if I look at g sub 2 and g sub 1, there's a constant ratio between those two terms. Okay? That constant ratio represents our r value. So let's take a look at this first example. It says give the first 6 terms and the constant multiplier in the geometric sequence g, where g sub 1 is equal to 5 and g sub n is equal to 4 times g sub n minus 1. Now let's not forget what g sub n minus 1 means. It just means the previous term. So if I'm finding g sub 2, g sub n minus 1 would be 5. So if I'm going to generate that sequence, the first term is 5. The next term is 4 times 5, or 20. The third term is 20 times 4, or 80. So we're always taking the previous term times 4 to get the next term. So I've got now 80 times 4, which would be 320, which would be 1280, which is 5120. Now it also asks us to identify the constant multiplier. Well, the constant multiplier is that value of r, and that value of r is this 4 here, so that value would be 4. Now, we can use our calculator to generate these sequences as well, and the way that we do that is we enter the first term, which is 5, and then we're going to take that times 4, so I'm going to go times 4, and if I hit enter, it will give me that value, and then I can just keep hitting enter, and it will continue to generate the sequence for me. So just like with arithmetic sequences, we can generate geometric sequences both recursively and explicitly. So the next thing that we have here is the explicit formula for a geometric sequence. And to do that, it says in a geometric sequence with the first term, g sub 1, and a constant ratio of r, each additional term, g sub n, is equal to the first term times whatever that constant ratio is raised to the n minus 1 power. Okay? And that's for integers greater than or equal to 1. There's two things we need to know. What is the first term? And what is that constant ratio? If I know those two things, I can generate the sequence. So let's take a look at number 2. In number 2, we're looking at using the explicit formula for a geometric sequence. It says the following. Write the first, 5th, 10th, 20th, and 25th term of the sequence A defined by a sub n is equal to 3 times negative 2 raised to the n minus first power. Okay? Well, really, if I'm going to do that, all I'm doing is finding out what is a sub 1, what is a sub 5, what is a sub 10, etc. Okay, so for each one of those, I'm plugging in. Remember, the sub number is the value of n, so I'm plugging that in for n into this function. Okay, well, since it is a function, just to kind of ease our calculations a little bit, one of the things we can do is we can use our calculator and actually define that function, and then use the defined function to find the ones that we're looking for. So what I've done is I've gone to, and I just typed in define, but you can also do it under actions, menu actions, define, and that will allow you to define a function there. So I've defined it in terms of the inside of parentheses here. This n represents the variable that it's defined in terms of. So a of n, or a sub n, is equal to 3 times negative 2 raised to the n minus first power. Okay. Now, if I want to find the value of that function at any value of n, I type in a, and notice how it comes in bold, knowing that it's an already defined function. So if I want to find the first term, I can put 1 in, hit enter, and it will give me that value, which obviously would be 3, because negative 2, that would be raised to the 0 power, which is 1. 3 times 1 is 3. Okay. So if I want to find the fifth term, I can say a sub 5, which is 48. I can then go a sub 10, which is negative 1,536. Then we want to find a sub 20 and a sub 25, and that would represent those 5 different values. So obviously when you start raising something to larger and larger powers, that number gets big very, very quickly. Alright, so let's take a look at example 3 here. It says, suppose a ball is dropped from a height of 12 feet and bounces up to 90% of its previous height after each bounce. A bounce is counted when the ball hits the ground. H sub n, let H sub n be the maximum height of the ball after the nth bounce. Refer to the diagram below. Find the explicit formula for H sub n. Well, let's do that. So H sub n is equal to, now we're trying to write the explicit formula, and remember that explicitly it will always be equal to the first term times that constant ratio raised to the n minus first power. So that's what we're looking for. Okay. So the first term, we have to be careful. It is not 12. Because remember, H sub n represents the height of the ball after the nth bounce. Well, 12 feet is before it bounces at all. So here's where H sub n is. So I have to find that by taking 12 times 0.9 to get that height, because it's 90% of where it was, or excuse me, of its original height. So what I'm going to do is I'm going to use my calculator and take 12 times 0.9. If I do that, you can see I get 10.8 for that value. So that's what I'm going to use for my first term. Now my constant ratio is this 90%. This is R, which would then be, in terms of a decimal, would be 0.9. So I'm going to have 0.9, and then I'm going to raise 0.9 to the n minus first power. So that would represent the explicit formula for the height of the ball. Okay. Part B then says find the maximum height of the ball after the sixth bounce. So when I'm doing that, I'm finding H sub 6, which would be 10.8 times 0.9 raised to the fifth power, 6 minus 1. So if I plug that into my calculator, 10.8 times 0.9 is raised to the fifth power, I get 6.37729. So that would represent the height of the ball after the sixth bounce. Okay, for this last example, it says write a recursive and explicit formula for the following sequence. So knowing what you know about geometric sequences, keeping in mind that you need to know what the first term and what that constant ratio is, see if you can write a formula for this recursively and explicitly. Bring it to class and we'll go over the answer to that in class next time.